In this video, we'll move into Chapter 10 and cover our last topic left in statistics. This last topic is called hypothesis testing. Now, we've already seen in Chapter 9 the idea of trying to use sample information, sample data, to tell us about the entire population. That was the entire point of the confidence intervals, to use that value to not find exactly the population mean or population proportion, but to have an interval and know that it falls between those two values. Now, with hypothesis testing, now we're going to use sample data to test a claim. So we're still using sample data, and you'll notice once we get into the problems themselves that these are still very long word problems, but the overall nature is completely different. The previous unit, again, we always had that note, find the confidence interval. Find the confidence interval for the average amount of money spent in the store. Find the confidence interval for the average amount of time spent studying, or for the average score on the exam. It was always very clearly stated. Now with hypothesis testing, we're going to have to read a little more carefully because it's not going to say, do a hypothesis test. There will be some generic language about testing a claim, but we really have to read through the problem. But all these problems, it'll always be about trying to test something. Maybe there is a new medication. Does this new medication help cure the cold faster than the old one? Will we get better faster? Or maybe it's a physical therapy treatment. If I do this technique, will that help improve my shoulder faster than the old one? Maybe I've implemented some new software, thinking more of a business example. I've implemented some new software, or I've changed my sales technique. Does that make a difference? And does that increase my total sales? Does that make me more money? Maybe I'm looking at a new group of students, or maybe I'm testing a new teaching strategy, and I want to know, does these new group of students, are they better than the previous? Or does this new teaching strategy, does that make a difference? Are students performing better than they were before? So through all these situations that I've described, and again, I'm just scratching the surface, and we're seeing examples from medicine, we're seeing examples from business, we're seeing examples from just everyday life. So all these examples are all gathered around that we used to know something, or we used to assume that we knew something about an entire population, but now we're looking at some, again, new technique, new group of people, and with that sample data, is that enough? Remember, this is a science. This is not just a random, well, I only tested 4 people and they got better faster than the people I didn't test. Well, I only tested 4 students, they did better than the rest of my students. All of this, how do we know, is that enough? Did you test enough people? Is that a strong enough conclusion? That's what we get into in this section. So again, everybody, this is a very deep concept, and this is really used in all different fields. So I'm doing this video just generically for Chapter 10. 10.1 is a little bit more of an introduction, and we'll get into more of the basics. In just a moment, I'll define the null and the alternative hypothesis. And that first section really tries to get us into that first piece. A little bit of notation, but kind of like the confidence intervals, we may finish with a little bit of notation, but we have to understand the sentence that goes with that answer. And that's going to be the same thing with hypothesis testing. We'll see some notation, but can we explain what is it that we used to know versus what is the new challenge to that original thought? And then to be able to make the final conclusion. 10.2 focuses a little bit more on the errors that are made here. They talk about the type 1 versus the type 2 errors. I'm not really interested in distinguishing between the two. We just don't want to make mistakes. We want to set up our hypothesis test correctly and then make the right conclusions at the end. 10.3 does hypothesis testing for proportion. So similar to the confidence intervals, I want to mention it, but I'll save that for the end of the video. And most of this is really about section 10.4, hypothesis testing for the mean. So that lays out everything in this chapter. And again, we've tried to, build some motivation. Very good idea to read 10.1 to start to see more of these different situations, start to become a little bit familiar with the language. But now we're going to start getting to work. So When we do hypothesis testing, we always start off with two hypotheses. I'm going to basically show you that hypothesis testing can be set up as basically a 4-step process. The book does similar. They don't always count them the exact same number. Sometimes they say it's 5 steps, sometimes it's 6. But again, it's really all the same idea. And step 1 is always setting up our hypotheses. And now there's 2, so that's hypothesis, but there's always going to be 2 of them. Notationally, we'll use this H sub 0, and that stands for the null hypothesis. These ideas, both null and the alternative, they're defined right at the beginning of 10.1, and the book uses very similar language to what I am, just being a little more informal here. The null hypothesis is what we currently believe to be true. Sometimes it'll kind of be what we used to believe, but the idea is really, what is the current thought on this situation? How long does it take on average to recover from a cold with the present medicine? How much money do we make on average? What is the average test score? If we're testing products, what is the average gas mileage for this vehicle? What is the average computer speed for this processor? So there's all these little things that we can do, but the null hypothesis is the current belief, what we believe at this moment. And for us, since we will only be hypothesis testing the mean, our null hypothesis will always have a mu. We'll always be looking at the population mean, and we'll always consider what does that average equal. So again, it'll all come from what we used to believe to be true. What is the average length of time to recover from a cold? What is the average amount of money saved? What is the average amount of money made? What is the average test score? All those things, the null hypothesis will always treat as mu equals. Now, I do want to mention some books will do, it can be a mu is greater than or equal to, or a less than or equal to. That's a part of just slightly simplifying. We'll always treat the null hypothesis as an equality. But now, this is still all a part of step 1. And again, that's why we're really setting up 2 hypotheses. The null hypothesis, what we used to believe to be true, and now H sub A will be the alternative hypothesis. This is the challenge to the original. Okay, that's how I'm going to phrase it. The challenge to the null. The challenge to the original belief. But when we challenge this, we're not going to say, well, you think the average for the population is this, I think the average for the population is that. The alternative hypothesis will always be a comparison to the null, to the original. So the alternative will still always have a mu, but will either have a less than, a greater than, or a not equals to, and it'll always be to the same value. So let me go back to that cold medicine example. If the present cold medicine says you'll be better in 7 days, well then mu equals 7. An average of 7 days for you to get better, mu equals 7. Well, I say my new medication cures a cold faster. Well, I will have for the alternative hypothesis, mu is less than that same 7 days. That is how we will set this up. I won't say I know what the new average is. I will just say I think the new average is less than the old average. And in some of the other examples, I think my new software will make the company more money. Well, this is the average the company used to make. Well, now I'll have mu is greater than that same number. That is how we set up the alternative hypothesis. And we don't just make less than or greater than based off of the data. We base it off of what people directly say. I think you will get better faster with the cold medicine. That's why I use the less than. I think we will make more money with the new software. That's why we'd use a greater than. But if I just say, I think this number is wrong or inaccurate, and I never give you any indication, or again, your researcher, whoever is making this claim, if they never clearly say that they think things will be better, faster, stronger, any of those synonyms that we could translate into less than or greater than, that's when we will use a not equals to. So that's 10.1, everybody. That sets these ideas up. And even though I'm just introducing this, going back to those original examples, I keep trying to read these in sentences. So if we see something, again, going back to the cold medicine example, mu equals 7 days, we have to interpret that because that's all we'd see here, but we'd have to understand, well, the belief, current belief, is that you will get better from a cold in an average of 7 days. And then to read these, well then, less than 7 or greater than 7. So we just see a simple line, but there's always a sentence behind that line. Okay, so now, all that, just step 1. Now we move to step 2. After we set up our hypotheses, we will then set up what I refer to as our critical region. And what we're going to do here, we are going to draw a normal bell curve. Again, we've been doing this a lot. And this still, everything we're doing here, chapter 9, chapter 10, really goes back to chapter 8 and the idea of the central limit theorem. What I'm doing is I am setting this up so I am comparing my sample data to compare to my population data. So that's where all those same ideas from chapter 8, when does the central limit theorem apply? Is this new distribution normal? Well, even if the original data is not normal, it can be normal if it meets certain circumstances. So again, I'm not trying to challenge you on those parts. I'm just trying to connect the dots. That's why we had to discuss chapter 8, because it keeps coming up. Okay, so now I set up the critical region. So I always set up what looks like a bell curve, even if it's not perfect. Even if it's a T distribution, the bell curve will still work. And now our critical region is one or both of the tails. And it all comes back to the alternative hypothesis. If your alternative hypothesis was mu is less than, then your critical region will just be the left tail, the tail that is less than the actual mean. But if you're in the second situation, that your alternative hypothesis is mu is greater than a number, well then it would be a right tail. So let me even make that note over here. So HA, mu is less than, that's my picture. HA, mu is greater than. Now I've got the right tail, and the last possibility, if HA, if the alternative hypothesis is a not equals, then we will get a two-tail test. And what I keep shading, that is what we refer to as the critical region. Now here, at this point, I do a slightly different technique than what the book does. So when we get to solving some problems, I will point this out. But what we will get here, this shaded area, we will always get alpha, which we will also refer to as the level of significance. And that will always equal the total area in your critical region, the total shaded area. So in this first case, alpha is entirely in the left tail. So if alpha is 0.01 or 0.05, that area goes exactly right there. And similar, if I have mu is greater than, then alpha is entirely in the right tail. But then the last situation, this is by far the most common mistake. If you're in this last situation, alpha has to be split up equally so that you're getting half alpha in the left tail and half alpha, and half alpha in the right tail as well. So if alpha is again 0.05, which would be given in a problem, The only thing that might come up, sometimes they'll literally tell you alpha equals, other times they'll say use a level of significance or testing at a level of significance, but that number will always be given in the problem, similar to the way the percentage of confidence was always given in our confidence interval problems. So that is always going to be the setup. So if alpha is 0.05, this area is 0.05. This area is 0.05. But both of these would be 0.025. I took the 0.05, multiplied by 1/2 or divided by 2, same thing, and put that value in each side. And we're still not done with this part, because now we're going to need the critical value. So we set up the critical region, there's our alpha, and now we'll get a critical value, and that value will be Z or T. We'll have to figure out if we should use Z or T, and this is going to be just like confidence intervals. It's going to come from the standard deviation. If I know the population standard deviation, we'll use Z, and if I know the sample standard deviation, if I don't know the population but only know the sample standard deviation, I'll use T. And the way I will get these values is by going back to either our T chart or our Z chart. And most people would actually use this side of the Z chart. But here's the funny thing, everybody. If you're using Z, look at this one, you know the area in the tail, you'd have to find the Z that goes with it. That means you're looking for the closest area inside of here and pulling back to get the appropriate Z score. So again, that's something we did back when we introduced the normal bell curve, and that's something we'd have to do here. But in that section, that was our only choice. The real idea, everybody, again, you could use this if it's Z, but a lot of people always use this chart for this section. T or Z, this chart will work. But here's the difference, everyone. When you've got these alpha values that I'm talking about, and I'm pointing them out over here in the picture, we have to make that work with this picture. So these regions across the top, we used to just use the confidence level in these percentages, but these percentages go exactly with these middle areas. It's not the area entirely to the left. It's not the area in the left tail. It's in the middle area with these two tail regions being equal on both sides. So if you use this picture, you just have to figure out the appropriate middle area based off of your alpha values. And then if it's Z, we'll just go down to the bottom and pull the Z from here. Notice it even calls it a Z critical value. And up here, a T critical value. That's exactly what we're getting right here. That's exactly what we want this for. So if it's a Z, we just get the appropriate middle area and come down to the bottom. But if it's T, we'll still have to do that work to get the appropriate middle area, but then we'll still have to consider the degrees of freedom. And this is just like the confidence intervals. That will just be n-1. So if I knew I had 0.05 as this alpha and that's it, to make this graph work, I'd have to pretend there's another 0.05 here, and I'd have 0.90. 5% here, puts 5% here, leaves 90% in the middle. Whether you do that as decimals or percentages, either way gets me to here. And if it's a Z, my critical Z would be 1.645, the end. If it's a T, well, I'd also need the degrees of freedom, and I get the appropriate value from here. All of these always come out positive. It's up to us to realize, and that's what it points out here. If you're over here, you need to realize T or Z is negative, and over here, T or Z would be positive. So again, everybody, you're seeing I'm going through very generically, just another 2 minutes, and then we'll start to do some actual full problems to see this for ourselves. But this is a very long process, but it's a very repeatable process. So, critical region, how do we know critical value if we do Z or T? Well, we have to look ahead a little bit and know about Do we know the population standard deviation? Then we use Z. Or sample standard deviation? Then we use T. Step 3. Now we will find our test value. And this is where we will finally use our sample data. And this also goes back to the central limit theorem. We have the test value, and some people like some little subscripts to distinguish these two. They use a Z sub C for the critical, a Z sub T for the test. I don't mind if you don't do that, everybody, just as long as we realize we're getting 2 Z's or 2 T's here. But this Z was coming, or T, is coming off the chart. This Z or T is coming from a formula. And for Z, we'll still use the x bar minus mu divided by sigma over the square root of n. Or if it's T, it'll be x bar minus mu s over the square root of n. By the way, this formula was given to us back in chapter 9 when they introduced the T distribution, but I didn't mention it because we didn't need it until this point. But the T value serves the same purpose as the Z, but again, it just goes with the distribution when we know sample standard deviation. We still have N as our sample size. Now, finally, now that we've got all of that, step 4, we make our conclusion. And there is 2 possibilities here. We're ultimately going to be comparing the Z or T we got from here to the Z or T we got from here, because it's all about the 2 possibilities for your conclusion. Conclusion number 1, if your test value is in the critical region. So I've already marked this off. So if I know my critical T or Z is, say, 1.96, but then my test T or Z is 2.13, well, 1.96 is here, 2.13 would be further to the right. I am in the shaded region. If that happens, we reject the null hypothesis and accept the alternative. Basically, what that is telling us is that the alternative hypothesis was correct. We have enough information to conclude that this is right, while this old belief, maybe again it's just wrong because of new information, but we have successfully challenged the old belief. So, that's my first conclusion, but now when I go to write up my second, such a common mistake. Well, if I'm in the critical region, that means the original idea is wrong and the new idea is correct. So now people go, well, if I'm not in the critical region, then the original idea is right and the new idea is wrong. But that is not how it goes, everybody. If that happens, so now my test value is not in the critical region. All we do in this situation, failure to reject the null. We don't reject the alternative and accept the null. It's a failure to reject the null. This is a little silly the first time you look at it. It's almost like we never admit defeat. It's almost like, okay, it doesn't look like I'm right now, but maybe there's just not enough information. And that's almost always how people write this. This idea of failure to reject the null, again, they don't say the null is right. Going back to my medical example, I don't say, oh, it is correct. It takes 7 days to cure a cold. All I would point out is my failure to reject that. There is not enough information to confirm this fact. So I'm not confirming this, I'm just failing to reject it and failing to accept this one. Those are the 4 steps, everyone. So I'll set up another video so that way we'll have a separation so you could look at this for the instruction, but the next video we'll start doing the actual problems. And the very last thing, which again, I will point out after the next video, I'll come back and point out that this will be the same exact idea for proportions, that is for means, and that at the end here, just a little bit more about making conclusions. Oh, actually, I'm sorry. I wanted to come here very quickly just to point out both of these formulas are where the error formulas came from when we did our confidence intervals. That we just multiplied this to that side and we looked at this distance, this difference as the idea of error. So I just wanted to point that out quickly. But again, at the end of, in the next video, we'll do some full problems, getting used to this idea, all the steps, setting up the hypotheses, reading through the problems, understanding all the details, and then making sure we make the right conclusions at the end.